YouTube for the Center for Integrated Quantum Materials, and if you look at videos, it's not just the seminar series, but it's all of those talks, plus other talks introducing these things. If I can get one of these to go, I can try myself and see if that works. It's quite dangerous. But you just click the one that you would like to see, like that, and courtesy of YouTube, it shows up. And what it shows are the slides plus the voiceover from the speaker. And by doing it that way, you can actually read the slides and understand what's going on. And we find that YouTube is actually really pretty reliable. We also stream these so that people at MIT and Howard University can see it in real time without bothering to show up here. We found that also works really well. Okay, that's all that I want to say. Let's get on with the show here and get our speaker wired in. I hope this works.
Oh, now the sound is on. Just.
Yeah, and for some reason I'm talking out of his computer, which worries me, but I think we'll fix that in a second.
Just stop it. Just close it. Okay.
Okay, good. So Dominik got his PhD degree in Munich in Germany, and then came here. He's working with Ron Walsworth on how to use nitrogen vacancy centers in diamonds, ultra-sensitive magnetic field sensors. He's going to tell us about that.
Thank you very much for the introduction. Okay, where's my stick? Yeah, today I would like to talk about a project we've been working on in the Walsworth group now for 3 years. It's about using diamonds as a quantum material for sensing NMR signals with very high spectral resolution. And before I start, I would like to thank, of course, Ron Walsworth, my PI, for supervising the project, and especially my colleague David Glenn, with whom basically this project has been done together, and co-workers like Paul Lee, who basically supported us with single NV experiments, and the 2 other PIs, Professor Lukin and Professor Hong Kong Park, and of course the funding, which makes this project possible. Let's start with some kind of history of NMR. So if you go through the Harvard Science Center, you might see at one corner this very old electromagnet. This indicates that Harvard has a very famous history about NMR spectroscopy. So 1948, Parcel, Blombergen, and Powell have done one of the most cited physics papers in NMR, and they use this very old electromagnet shown here. And what we are doing nowadays, so even 70 years after this, we're still working on NMR, and we still, you might see, use here an old electromagnet, which is again 60 years old, but the main changes are today that the sensor is different. So in these old days, basically, people used a coil for sensing these NMR fields. Nowadays, we're using a quantum material, the diamond, for sensing these NMR fields. And I will show you during the talk why this is better, or has advantages at least, in comparison to this classical detection method. Okay, here's the overview over the talk. So I would like to start explaining you why is NMR important, what is it good for. And then I will explain you the NV diamond quantum sensor, so how does the sensor work. Then we will talk actually about the first NV NMR experiments and what were the limitations of these. And then I will talk about our actual project to develop basically this high resolution NV NMR method. And in the end, we will shortly discuss some results and possible applications. Let's start with the first part. So it's a very basic slide here. So what's NMR spectroscopy actually? So if you bring a NMR active nuclei with a spin into an external magnetic field, it will start to precess. And the frequency of this precession basically is proportional to the magnetic field which is applied here, times basically a constant, the gyromagnetic ratio of this nuclei. And these frequencies are basically sensed in NMR spectroscopy, and these frequencies show up in an NMR spectrum like this. So this is, for example, an antibiotic molecule, and people would like, of course, to know what's basically the three-dimensional structure of this molecule when these compounds are, for example, produced. And down here is an NMR spectrum. You see many lines in here, and each of these lines basically corresponds to a proton in this organic molecule. And so people can go back from this relatively complex spectrum here to the three-dimensional structure. And therefore, it's one of the major tools in structure analysis of chemical compounds, especially organic compounds. The next few minutes, I would like to show you basically how to analyze these spectra and what information is in the spectra hidden. And let's start with a very much smaller molecule, like this one here. And the NMR spectrum of this molecule looks like this. So you can see basically 3 different lines, which indicates basically 3 different proton groups in this molecule. And NMR is a quantitative method. So what you do usually, you integrate these, the signal intensities of these peaks. And now this, if you believe me, it's basically 1 to 2 to 3. Also, it looks differently, but it's just these are broader here. And this means basically these proton groups have an intensity ratio of 1 to 2 to 3. And now if you look at the molecule, we basically can assign these lines to the 3 proton groups. Usually it's more complicated than this, but in this example, it's very easy because we know we have 1 proton here, we have a CH group over here, and a CH3 group over here. But this NMR spectroscopy contains more information. So one question is, for example, what's this axis down here? What is chemical shift in parts per million? What does this mean, basically? And as I said before, we measure basically the precession of these nuclear spins, proton in this case. But depending on the position of the proton in the molecule, the precession is slightly different. Because basically the electronic cloud around the nuclei basically is isolating or reducing the local magnetic field. And these changes, depending on the electron density, is very tiny, and this is like parts per million. Therefore, we show here on the scale parts per million. Just as an example, let's assume the proton resonance frequency is at 500 megahertz, like in many of the commercially available NMR devices. This basically means that 2 parts per million is 1 kilohertz in frequency. But you see basically these different frequencies, the frequency differences here are tiny. And basically, just remember, it depends basically on the electron density around your nucleus. And you see, for example, this proton here has oxygen in the proximity. This means electron density is basically withdrawn, and this moves basically your proton into higher chemical shifts. This is just a definition down here. And the important thing is that because it's parts per million, so this chemical shift is always field dependent. Therefore, it's a fraction of the applied field. Right, and you can see here the equation for this. So the frequency is basically then not only proportional to the applied field, but also on this shielding factor of the electron density here. But there's more information in this NMR spectrum. If we zoom in to these resonances here, we will see that they have a special pattern, basically. And this is just 1 line, but these are 4 and 3 lines. And these are basically, this pattern is caused by the coupling of 2 protons. So we call this J coupling, and this is coupling basically along the chemical bonds, so basically mediated by the electronic clouds in this molecule. And just looking basically at this pattern, you can, for example, deduce that both of these protons here, or proton groups, are coupling to each other, which causes basically a quartet and a triplet here. And this is just based on the possibilities how you can align, for example, 2 spins in external magnetic field or 3 spins. So as I said before, we basically detect, or these magnetic fields generated by these nuclei are detected by coils which you wind around your sample, for example. And this brings us now to a major drawback of these techniques. So usually you need a lot of sample, like this is an NMR tube for these commercial available NMR devices. So you usually need like hundreds of microliter of sample for doing NMR spectroscopy. This is, of course, a major drawback if you are sample limited, but it's also a major drawback, for example, for actually basic science. If you want to think about, I would like, for example, to measure a single cell or a single molecule with NMR spectroscopy. And this was not possible because you can just think that you cannot make your coil, smaller than tens of microns, or even on the nanometer scale. This is just the limitation. And now we come basically to the NV diamond. So the new tool now is not the coil. So basically we try to replace the coil with diamond. And actually, sensor is not the diamond itself, but it's a defect in the diamond, which is basically fluorescent. So you see here, for example, our diamond looks like a chip. For example, this one is 4 by 4 millimeters. And if you shine green laser light on this diamond, it will basically emit red light, which is shown here. And this is basically then our sensing. So sensing method, the fluorescence light will change up in different magnetic fields which are applied at this diamond. Okay, so the next thing, let's go through how this NV diamond quantum sensor actually works. So we call this defect in the diamond nitrogen vacancy center because in the diamond lattice, which is basically indicated by these black balls here, which are basically carbon atoms, one carbon atom is replaced by nitrogen, and one carbon atom is basically replaced by vacancy, so there's basically nothing there. And therefore, it's called nitrogen vacancy center. And these NV centers can be formed either by basically incorporation during diamond production. So for example, you also add some nitrogen in your production synthesis, and then basically this will basically build into the lattice, and then you anneal the diamond, and holes basically in this nitrogen will basically get the proximity, and you form this NV center. Other possibilities are, for example, you basically shoot ions, nitrogen ions on your diamond, and then do the same thing with annealing so that the nitrogen atoms and, for example, the vacancies find each other. So what are the properties of this defect now? The important thing, it's a triplet ground state. So this means basically we have the MS0 and MS plus minus 1 values, which are basically energetically separated by a zero field splitting. And this defect absorbs green light, as I said before, and emits red light, again shown here as an example. And the important thing is the photophysics now. And if you, for example, go from this MS plus minus 1 state into the excited state, this state has a certain probability to decay via a singlet state, which is dark basically, and then decays back to the MS0 ground state. So this has now two important consequences. The first one is basically that we can optically distinguish the MS0 state from the MS plus minus 1 state. If we excite from here, basically the only option we have is going back down here. So this gives us high fluorescence, whereas in this state here, we have always a certain probability to go via this intersystem crossing channel down here. So the fluorescence rate from this state is lower than here. So basically, this state is brighter than this state here. So we can optically distinguish these two states. In addition, is also that we can optically initialize the state. The reason is because if we excite here, in the MS plus minus 1 state, we will end up in the MS0 state. So this means if we shine laser light on the diamond, on this defect, and we basically cycle through this excitation and fluorescence procedure, we will always stay in MS0 state if we start here. But if we start in the MS plus minus 1 state, we will go basically into the MS0 state. And so basically all of the population accumulates in the MS0 state. So we can optically basically define our initial quantum state, which is then the MS0 state. And furthermore, we can also access this transition here with microwaves. And this gives us an effective two-level system where we can use microwaves to manipulate the spin state in a coherent way. So the easiest experiment you can think of is you basically shine green laser light on your diamond, on the NV centers, and basically detect the red fluorescence light. And this means, basically, as I said before, if you shine laser light on this diamond for a certain number of time, you will always end up in the MS0 state. So basically, if we now normalize the MS0 state to 1, this is basically the fluorescent MS0 state. Now, if we basically place a wire next to our defect and put in a microwave, which we sweep the microwave frequency, we will see that when we are off resonance, nothing will happen because we can't access this transition. If we are on resonance, basically, we will jump from the MS0 state to the MS plus minus 1 state, which is basically darker. And this means we get basically a dip in the fluorescence over here. This is now exactly at this zero field splitting, what I mentioned before. And now we can use this as a magnetic field sensor by applying, for example, external magnetic field, which splits up, the CMAL splitting, both of these states here. And if we now again sweep the microwave, we will see that basically 2 dips appear in our data. And of course, the splitting of these 2 lines depends on the external magnetic field, and this can now be used as a sensor for sensing magnetic fields. in this case, especially DC fields. So, and this is not the main topic of this talk, to measure DC fields. In this talk, we would like to talk about NV NMR. So we are mainly interested in measuring AC magnetic fields, so alternating magnetic fields. And the question now is, how can we sense these AC fields with NVs? With the method I showed you before, it's difficult because we can, as I said, only measure DC fields. And the frequencies for the AC fields in NMR are usually like megahertz to gigahertz, so that's too fast to use the method I've shown you before. What we need now is like NMR or pulse sequences, where we basically coherently manipulate these states down here. So that's again the scheme of the NV center. And let's zoom into these transitions down here.
Wait, I'm sorry.
Sure.
A quick question. So the first time you swept, you had a single peak, and then the second
Right.
time
Yeah.
you
Let's go
had
back.
two. So I'm sorry. Can you just? I'm stupid, but remind me what the difference between the two.
Right. So we apply an external magnetic field. So if you have no field applied
this is
externally,
the B to zero case.
right? Yeah.
And then when you apply
Right. Yeah.
negative,
These split up basically these two states, and then basically get two transitions. Right.
Okay.
And this splitting basically depends on the applied field.
Great. Thank you.
It's for DC sensing, right? Okay, but now it's about AC sensing, so alternating field sensing. We zoom in, as I said before, on these transitions down here. And what we do now, basically, we access this transition here with microwaves and use a pulse sequence. So what I mentioned before, of course, is since we have this two-level system here, we can represent these two levels basically on a Bloch sphere. And of course, we know that all of the quantum states are available on the surface of the sphere. And we can basically do all of the manipulations, what we want to do. In this example, in the Rabi example, which is basically the most basic experiment for these applications, is that we use a short laser pulse to polarize the NV in its ground state, in the MS0 state. This means on the Bloch sphere picture, we just defined that the MS0 state is on the north pole. And then basically we apply a resonant microwave pulse where we sweep the duration of this pulse. And at the end, basically, we again use a laser pulse to read out the fluorescence and basically determine in which quantum state we are ending up. And then the easiest case is, let's assume we don't have any microwave. This means basically after polarization pulse, we are in the MS0 state up here. And we again normalize this just to 1. And this is basically the bright state, which MS0 state. And now if we apply our microwave and where we basically sweep the duration, we know that we get basically the Rabi oscillation. So the fluorescence will go down to a certain point, which is then basically the MS1 state, which is basically, we call this the state which is basically not as bright. We will go up again to the MS0 state again, and so on. And this experiment is important because we can now calibrate two pulse durations, which the NMR community usually calls like pi and pi half pulses. So what are these pulses? The pi pulse basically mean that we go in the Bloch sphere from the MS0 state to the MS1 state, so 180 degrees shift of our spin vector. And the pi half pulse is basically a 90 degrees shift of our spin vector to an equal superposition of the spin MS0 and MS plus 1. And these pulse durations now, the pi half and pi pulse, can be used to do a spin echo experiment. Again, we have first a laser pulse, which basically polarizes our NV center into MS0 state. The first pi half pulse then basically brings the spin vector down into the equatorial plane. And now we have a free precession time where basically the spin state can freely evolve. And if we're thinking of an ensemble of NVs, each NV has slightly different environments, so these spins will basically dephase. Then we apply a pi pulse. This means basically 180 degrees shift of the spin vectors. And again, we leave the same time to evolve. And then basically, since we have a spin echo, all of these spins rephase. It's a typical spin echo experiment. And at the end, basically, we use again a pi half pulse to project or to transfer this coherence into a population difference, which we then can read out optically with our NV. And of course, this rephasing, what I told you about here, depends basically on the time spacing here. So the longer we make, the more unlikely it will be that this rephasing is efficient, because these two times won't be identical. Of course, it depends. The time scale depends on the noise of your environment. And a typical T2 experiment of an ensemble of NVs is shown here, and we see, for example, that this T2 time is something like 8 microseconds for this ensemble of NVs. And now, of course, the question is, how can we use this experiment for sensing AC fields, like NMR signals? Well, let's think about how can we basically influence the coherence. Let's assume we have an AC field generated either by a coil or a nuclear spin, and basically half of the period coincides with this free precession time here. What will happen then? Well, we again tip down the spin vector on the equatorial plane with our pi half pulse. Now, basically, the first free precession time, let's assume the B field points up, so we'll get some phase accumulation. Then again, we basically apply a pi pulse, flip the spin over 180 degrees. But now, for the second free precession time, the direction of the B field has also changed. So this means basically we don't echo out this phase accumulation, but even we get more of this. And if we now project back, we will see that we don't end up in the MS0 state, but in a superposition of both of these. And this means basically that we get a dip in the fluorescence signal, which is shown here, for example, for a very shallow NV layer. So this means the NV sit basically 5 nanometer deep of the surface of the diamond. On the diamond surface are protons in oil. And if we do this T2 experiment, we will see at a certain free precession time here a dip. And now, of course, we can calculate from this free precession time the frequency. I can also subtract this background decay here. What we will see that we basically get a resonance peak at, for example, around 1.4 megahertz, which exactly fits to the proton resonance frequency at a couple of hundreds of gauss.
Wait, so you're externally driving the external AC-B field in coordination with the microwave pulses.
Right. So you have to. So right.
Basically, exactly half a some. Is that a coincidence in how you're drawing it? Or
Say it again. Say it again.
So you're basically linking the phase of the oscillating
So
magnetic
that's
field to the microwave pulses.
No, usually it's not the case. So usually, I will talk about later, it's spin noise, so the phase is arbitrary. But you will always basically decohere your NV. So even if you move this around, for example, you will still get a decoherence here. But usually the phase is not fixed, for noise experiments. This will be essential for the later part of the talk. And just to get a feeling, what's basically the sensing volume we are measuring. This is unfortunately a bad scheme, but basically the radius of the hemisphere here is basically the same distance like the depth of the V for the surface. So if, for example, your NV is 5 nanometer deep, also this radius of the hemisphere is also 5 nanometers. And you see these experiments now detect really basically NMR signals on very small length scales, which is very new in comparison to the old NMR experiments. And now just some applications from the looking group. So what can you do with this technique? For example, you can look at a single layer of bodonitride and compare it to a bulk layer of bodonitride. And what the group has found out, for example, that the resonance frequency of these borons and nitrogens basically moves around. And so you can see that basically the electronics and the structure changes if you go from a single sheet to a bulk sample. Or the other example is, for example, you can look at proteins. So what you look here, basically a single NV, and basically place a protein next to the single NV and can then detect, for example, carbon-13 or deuterium signals from the single protein. Now, what's the drawback of this technique? As I said, you can definitely measure on smallest length scales NMR signals, but if you look now at the line width of these samples, it's usually like tens of kilohertz. And if you compare this to the part I've shown in the introduction, what we really need basically for doing this high resolution NMR spectroscopy to distinguish different proton groups in a molecule, we need something like 50 hertz, or basically hertz resolution to basically distinguish these 4 lines here. And now that's basically the part when I started here in Ron's group to solve this issue and to develop basically a high resolution NV NMR technique. So let's again, overview. I show here the spatial resolution. So basically, let's go from millimeter to nanometer. And here basically the spectral resolution, so the line width basically. You see these traditional NMR methods like NMR, and there's some microcoils available, basically probe on the millimeter scale, maybe hundreds of micrometer scale. And this original NMR, NV-NMR experiments from 2013 basically probe signals on the nanometer scale. But the issue of this method here is you see that we get these broad lines, and so all of this chemical information is basically hidden in these very broad lines. And so the aim was to, or the goal was to basically develop a technique which basically works up here. We basically get high spectral resolution on much smaller length scales than conventional NMR. So what's basically the difference between this NV and this conventional NMR? Well, let's first think about what's actually the NMR signal. What do we detect? What we detect is basically the polarization of nuclear spins, which is basically defined as the difference of spins up and spin down divided by the total number of spins. This basically gives you the signal intensity. The higher this is, the bigger your signal is. And you can think about this. We can calculate this for room temperature, like it's the Boltzmann distribution. That's the temperature. That's basically the energy gap of spin up and spin down. And since this energy gap is very small, this thermal polarization is usually very, very small. And for our case, so we work at the moment at sub-Tesla magnetic fields. It's like 10 to the power of -7. Even if you would go to very big electromagnets, the best case what you get is something like 10 to the power of -5. So the number of, the fraction of spins polarized in the sample is always very, very small. But it works for these big samples because you have still a significant number of spins which are polarized in your volume. If you now go to smaller and smaller volumes, for example, let's pick up like 10 by 10 by 10 nanometers, a cube of these length scales, there's roughly 10,000 spins in there. So if you think just of this number, with a polarization of 10 to the power of -7, this means basically that none of these spins is polarized in this volume. So we never can basically detect thermal polarization on small length scales. So how do these experiments actually work? Well, since we have a very small, let me first finish this here. If we have these spins polarized, the usual way to detect these is we tip them over, so they're polarized. You tip them down with a pi-half pulse, and then you get the free induction decay, which is then sensed with coils, which I mentioned at the beginning. Right. So this experiment doesn't work on the small length scales because we don't have enough spins in our volume to get a significant polarization in there. However, why do these experiments still work? Well, since the number of spins is small, you have basically spin noise. So the spins are randomly orientated in your volume, and you will always have some polarization of your spins. And you can calculate the spin polarization basically by the square root of the total number of spins you have. And if you plot this here in the figure, you will see that this exceeds, for the small volumes, by far the thermal polarization. It's just because you have a small number of nuclear spins. And what you detect now is basically, as I said, it's spin noise. So it's basically just random fluctuations at the Larmor frequency of your nuclear spin. So why is this an issue for getting high resolution NMR spectroscopy? So the line width, if you detect the spin noise here, is limited basically by the correlation of your spin noise. And so what sets basically the correlation? Well, since we're probing a nanoscale volume, we have to think about diffusion, so physical diffusion of spins. And for example, if you go to water, the time it basically stays in this, let's say 5 or 10 nanometer sphere here, is just a few nanoseconds. So this basically means your Larmor frequency will be modulated on this time scale. This basically gives you the correlation, which is basically set by the diffusion constant of your molecule. And if you go, for example, for water, it's very short, like 10 nanoseconds. For like in viscous oil, it's like 100 microseconds. This basically gives you like line width from megahertz to tens of kilohertz. And this is basically the issue, or the main issue for this nanoscale experiment. You're just limited by physical diffusion of these molecules on the surface of the diamond. So how can we overcome this? And the basic idea we had to overcome this, the only way is basically to go to the thermal polarization regime. Because in thermal polarization, all of the spins behave identically. And so we said, well, where's this crossover for these low fields? And it's something like a few micrometer. And we planned basically to do our experiment basically, so to make our sensing volume bigger and go, for example, to 10 by 10 micrometer volume, where basically the thermal polarization exceeds the statistical polarization. Yeah, sure. So this is room temperature, like 20 degrees, and this is 0.1 Tesla. So that's the field where we are working at. As I said before, if you, of course, go to like 10 Tesla, 20 Tesla, you will go up to 10 to the power of -5. But I think that's the number usually you have for these big NMR devices. So it's still tiny, even if you go to, of course, if you would go to lower temperature, it might be different. But all of these experiments are usually done at room temperature because we want to have a liquid sample. Okay, so the idea was basically to go to the micron scale with our NV diamond, and then basically we switch from the spin noise to the free induction decay, where we basically can detect. And so how do we basically detect a 10 micrometer volume with NVs? So the basic idea is not to use single NVs, but to use basically a thick NV layer. So that's our diamond here, and the first 10 micrometer of our NV diamond chip has basically a very high dense layer of NV centers. And as I said before, as a rule of thumb, again, the depth of this layer here is also determines the volume of our sensing scheme. So that's basically just one issue of this NV NMR. The second issue is also the NV detection scheme. So let's assume now we have this free induction decay, we're in the thermal polarization regime. The issue now is that we can only read out this AC field, so this NMR field, as long as the spin state of the NV lives. And there are different detection schemes. I mentioned before this T2 experiment. You can extend T2 with applying many pi pulses. But the limit of basically doing this readout of this AC field is limited by the T1 time of this NV center, which is 2 to 3 milliseconds. And so this means even if we have a very long T2 star now for the nuclear spins, like 1 second, this gives us a Hertz line width, we only can probe like 2 to 3 milliseconds at the beginning because that's the limit of our NV sensor. So how do we overcome this? And this is basically the second part of the project is, well, we basically came up with a new pulse sequence, which we call synchronized readout. So how does the synchronized readout work? Basically to overcome the spin state lifetime. Well, again, we take an AC field generated either by a coil or a nuclear spin. Let's assume we do a simple spin echo. As I said before, usually we apply more pi pulses in here, but to keep it simple, we just use a spin echo here. So let's assume we are now totally in phase. And we basically get phase accumulation of these two fields here. And we read out again with the green laser light and detect the fluorescence. And now the basic idea is that usually we are limited by the T2 of the NV center. So we cannot read out this frequency only as long as basically the spin state of the NV lives. This basically sets our line width. To overcome this issue, we said, well, why can't we do like a synchronization? Why can't we repeat this experiment again in a synchronized way so that basically we exactly start at the same phase like here? So basically, the dead time here in between is like a multiple number of this frequency. And then basically we repeat this identical experiment several times. Of course, we always sense the same field because we have the same phase accumulation on our NV, and we get basically the same fluorescence signal. And this basically can be done for many more readouts, and we always read out the same value, and we will always get the same fluorescence value. If both of these, so the free precession time in here, has the same basically frequency like the AC field which we apply. And now the important point is that if these two frequencies are not identically, so slightly detuned, we will see an oscillation in our fluorescence data. Why that? So let's assume at the beginning what I've shown you before, we are basically have our pi half, pi pulse, pi half pulse. We are totally in phase. And now, of course, since both of these frequencies are not the same frequency, we'll always get, for each of these readouts, we'll always get a slight phase shift. So for example, if we look at a later time point, for example here, we will see that, for example, the external field has now a 90 degrees phase shift in respect to our spin echo. And this means right, yeah. So each of these readouts here, we integrate basically here like 1 microsecond of our light.
And that's enough to not have noise problems?
Well, it depends what you want to measure. You will see later, right? Yeah. Of course, that's a limit in the end, yeah. Right. So at the beginning, let's assume we are totally in phase. So if we look later time points, we basically will be like 90 degrees phase shift. And then you see, if you look here, the echo basically, we don't get any phase accumulation because both of these echoes are identically. So basically, we end up here. And then if we look, for example, at the later readout, we have 180 degrees phase shift, and so basically it's totally inverted, and so we get a minimum interference readout. And this will, of course, move on and on. Mm-hmm.
Point is a statistical average over many realization experiments.
No, it's just a single point. So let me just maybe move on one slide. So these experiments now have done with an ensemble of NVs, so we have many photons. And this was done now with just a signal, like a coil next to our diamond. In this case, for example, they have both the same frequencies. So the free precession time is basically the same time, like half of the period of our applied field. And if they basically have the same frequency as I said before, we see nothing because each of these readouts is identical. And we just always the same fluorescence. And you see, each of these points basically is one single NV readout. And now basically if we just turn the knob on our signal source and detune 1 Hertz, we will see that basically our readout, that's the time scale here again, that's basically each of these is one readout, will start to oscillate, and that's exactly, see, it's one full oscillation in 1 second, so that's 1 Hertz. So it's always basically, we see always a different frequency in our readout. And we can move on, like, detune it like 10 Hertz or 100 Hertz. And then we can take the Fourier transformation of this signal here, for example, we end up at 100 Hertz, and get a line width of 1 Hertz, of course, because we read out this AC field for 1 second. And we can push this technique even further. So for example, we can do this readout for nearly 1 hour. And then we can basically get a spectral resolution of sub-millihertz, which shows basically the capabilities of this technique, which is basically not necessary for doing NMR because usually you are good enough to have something like a Hertz line width. But this shows basically that this technique is not limited by any NV spin state lifetime. The only limitations is the stability of our clocks, basically, of the signal source and our pulse sequence. Okay, now let's show you the results and the application of this method. So the basic experiment looks like this. So since we have the thermal polarization, we apply a pi half pulse on the nuclear spins, like in traditional NMR. We tip the spins down. They will make a free induction decay, and this free induction decay will then be measured with this synchronized readout. So again, basically, each time we read out the NV fluorescence and plot this basically on a time scale, which is shown down here. So each of these points basically is one readout of this pi sequences here. And what we see, for example, is a sample of glycerol. So we apply over here this nuclear spin pi half pulse, and then we see here the envelope of this free induction decay of glycerol. We can take the Fourier transformation, and basically what we see is a resonance line at the proton frequency. We can move around this resonance by just changing the magnetic field and calculate from this the trigonometric ratio, which is exactly what this should be for protons. And if you look here, the line width is something like 30 Hertz. And the 30 Hertz, of course, is much better than previous NV NMR experiments, but it's still too broad, basically to detect this chemical shift and the J coupling. The reason why this is 30 Hertz is basically sample limited. It's just because the glycerol is very viscous and it has just intrinsically short T2 star times, so broad lines. So what we measured basically is water. So people know that water have very narrow resonance lines. And if you measure this with our technique, we end up with something like 2.5 Hertz line width for water. And this is now limited just by our experimental conditions. So we use an electromagnet, and this electromagnet has to be stabilized. And this is basically just the technical limit of the stabilization of our electromagnet. And now basically we can take like spectrum of small organic molecules, like this phosphorus compound here. And for example, we see that this has a line splitting of 13 Hertz. This is the first time people see like J coupling with NVs. And this splitting of here is just due to the two possibility how the phosphorus spin can align in the external magnetic field. So it's either spin up or spin down. This basically splits up your proton resonance frequency in 2 lines. Or we can look, for example, at xylene and can, for example, distinguish the protons connected to the ring or to these CH3 groups here, which are split by 20 Hertz. Okay, and that's just to sum up and show you an overview. So whereas traditional NMR gets this very high spectral resolution, and the NV NMR basically has low spectral resolution but high spatial resolution, we can basically fill up this gap up here. And the important thing to mention that we are not only limited to the micrometer scale, so we can either go to the bigger volume, but also, for example, to make this NV layer thinner, we could also go like for for example, 1 micrometer, maybe sub 1 micrometer, if you go to higher magnetic fields and still have thermal polarization. And possible applications we have in our mind is, I think what is obvious is single cell biology, because our sensing volume is at the moment defined by the laser spot size, which is something like 20 micrometer. That's one big application. Then the other thing we're thinking about is more like a commercial application, that we could build like a chip-based NMR method. So you have like a NV chip, and then you basically would probe like bigger volumes. So the NV layer would be like 1 millimeter, for example. So you would probe microliters, and people could just put a droplet of your sample on the surface of the diamond, and you can measure NMR from that. Or you could think also to make like a diamond chip where you can do many NMR experiments at the same time in parallel. So this would basically bring NMR spectroscopy for high throughput applications like in pharmaceutical industry, or of course material science, where we still do some brainstorming what this method could be good for. Also, if you have any suggestions, ideas, we're happy to discuss this and think about it. Okay, so let me summarize at the end. So what was what's the take-home message of this talk? So that NMR spectroscopy is the major tool for molecular structure analysis. The major drawback of this method is not very sensitive, so you usually need a lot of sample volume. And to overcome this, the NV center in diamond can be used as a magnetic sensor, which basically is an atomic size sensor, so it's good for probing small length scales. And that we came up with a new NV readout scheme, which enables basically now high spectral resolution and NMR spectroscopy on the micron length scale. This I would like to finish my talk, and thank you for your attention. Right, yeah.
Let us imagine that you take this to the limit where you have a single spin coupled to a single NV center, and somehow you manage to polarize that spin. Is there a way to still make it work, even though it's a kind of strong projection?
Probably not. So we were thinking about this. So you have, of course, like a back action on the surface photons, and so we don't think that it works really on the nanoscale, like tens of nanometers. This is probably the wrong method for doing really nanoscale NMR.
And there's no way to be clever about it, right? Because
we were thinking a little bit about this, but not too much, honestly, because we were more interested in this longer length scale. I think we didn't come up with which solves everything, but as I said, we mainly don't think about the nanoscale. That's the main issue why we haven't thought about this carefully.
And so to follow up to that, now instead of using a single target coupled to a single probe, you have a whole bunch of targets, an ensemble of targets, but it's coupled to an ensemble of probes on which you're doing a strong projective measurement. Is that a problem for the same reason? Could it, you know what I mean? Like somehow your NVs you have a bunch of NVs, they're all strongly coupled to all your targets.
Yeah. So I think the main difference that you're saying is that we are very weakly coupled. So the coupling is very, very weak, or basically the distance to most of the NVs is like micrometer length scale. So the signal is also, just to get a feeling, so the signal we detect is around 100 picotesla, so it's very, very weak coupling regime. Therefore, I think we are not prone to these things.
So you managed to do this periodic probing because you're averaging over such a large ensemble.
Exactly right, yeah.
Other questions?
So your resolution now is limited by the decay time scale of your free induction decay.
Right, yeah.
So that is basically T2 star.
Mm-hmm.
So I'm wondering, can you do some spin echo or try to run multiple hypotheses on those limit spin to extend?
Right, yeah. So they showed you before this water light here with the 2.5 hertz is actually a spin echo on the nuclear spins. So if we don't do a spin echo on the nuclear spins, we'll end up with something like 10 hertz, 8 hertz. And this indicates, since we can narrow down the line with a spin echo, that we have some gradients at the surface of the diamond. So this is actually done with a spin echo. I didn't mention this before.
Okay, but this is only shown with water molecule. For the other molecules, you didn't.
You could do this all the time, right? Sure. But it's relatively complicated for our experiment. But it's definitely feasible, yeah. This was a simple spin echo.
Other questions? I had one for, you get the resolution of 1 micron, how long do you have to integrate?
That's a good point. So that's also the drawback of this method, of course. So we basically measure depends on what you measure. So the glycerol takes like a couple of minutes to see a signal like an SNR of 3. If you go to water, it takes like, let's say, half an hour to an hour. And the issue is, since with the thermal polarization, you measure your free induction decay, but then you have to wait T1 of your spin. And the T1 is very long for water, and the T2 star is very short. So just to get numbers, so the T2 star is like 100 milliseconds, 200 milliseconds, but T1 is 5 seconds. So most of the time you just wait, and this basically makes, these experiments relatively, time consuming because of this difference between T2 star and T1. But this is a general issue in NMR method.
But that's a lot better than you do without.
Right, so for example, you cannot detect these on this length scales NMR signal with traditional methods. That's not possible. But yeah, but still, we have to work on the sensitivity. That's because it's a pure samples. That's of course to keep in mind.
Any last question?
For now, what's the advantage of using the traditional method over the diamond right now?
Well, so I think reprobing a smaller volume. So at the moment, for example, I think the best thing what you can make is like hundreds of micrometer, like microcoils. So basically, we are making smaller volumes. And I think one application what we are thinking about is if you want to do like parallelized NMR spectroscopy, like we have a chip with many samples at the same time you want to measure. If you have coils, the coils basically talk to each other, and this doesn't work. Since we have this optical readout, you can make a small chip with like 10 by 10 sample volumes and read at the same time the NMR signal. So I think that's also one advantage. But the main thing that we just can go to smaller length scales and not limited by coil fabrication.
To do it with conventional NMR to get sort of, I forget the numbers wrong, but sort of 3 microns you have to integrate all day. So it's long enough that somebody gets their PhD, but nobody buys the instrument. So this is orders of magnitude better. So it sort of opens up new truth. One last question, sorry, I cheated. Okay, now let's thank him again.